All right, we're going to do some real important calculations today, finding that value of the pH that we've talked about before that can help us to tell the difference between acids and bases. In order to do this, you should use a calculator. If you've got one like what we use in class, use it. If not, I'd still recommend you find a calculator with a log button that you can do 10 raised to a power on, so that you can follow along and try and push those buttons and make sure you understand what we're doing here to get these answers. So, we're going to be filling out page 6, and it is just a lot of calculations. But first, let's make sure we understand this pH scale thing. It is a logarithmic scale, so we are going to be taking some logs in our calculations. And those logs help us get rid of some of the messy scientific notation that we're going to be seeing our concentrations in. So we could make a scale that was based off of these scientific notation numbers, but somehow people just get afraid and scared when they see those crazy looking numbers. Even if it was telling us the same information, it wouldn't be as useful. So we used a logarithmic scale in order to get rid of the exponents, make the numbers a little bit more like a normal number, and then it made our scale a little more useful and relatable to everyday people. So we are going to be focused on the pH scale here, and as we talked about in our notes previously, this is how we can tell whether something is an acid or a base. But first we have to establish that at pH 7, right in the middle of our pH scale, is where we have substances that are neutral, that are neither acidic nor basic by default. They're nothing. And water is the best example of a neutral substance. So it is exactly pH 7, as long as it's pure water at 25 degrees Celsius. It's not an acid or a base. Now, if you remember from our podcast, what we said was that acids are lower than 7. So that whole side of the scale down there, less than neutral, is our acid side, and our base side is bigger than 7. So our bases are 7.01 all the way up to 14 and beyond. As I've probably mentioned in class, science has developed a little bit since this pH scale was first established, and we can actually go off the scale now. So there are some bases that are more basic than just 14, that go 15 or 16. We do have some acids that are so acidic that they go into the negative values of our pH scale. That can happen. We've just kind of accepted that the pH scale can keep going, but this is the kind of normal range for normal substances. Now, we also have this thing down here that is the pOH scale, and it technically is the opposite values as the pH scale. We're going to learn a little bit about what pOH mean. That would mean that we would have both of these scales. But if you notice, when my pH is 0, pOH is 14. There's 7 and 7 here, and then opposites again at the far ends. So no one uses the pOH scale in order to tell whether something is an acid or a base. We always use the pH scale just because it's simpler to remember 0 or anything lower than 7 or anything bigger than 7. Just memorizing one thing, because if we have a pOH, we can always turn it into a pH, and that's exactly what we're going to be doing here today. So let's take a look at some of these equations that we've got in this big mess of equations down below. The first two I want to talk about are the pH and pOH equations. This is how we calculate pH and pOH. And what we do is take the negative log, and that's just a button on your calculator, of the H plus concentration. And you see that H plus in square brackets all over the place, and we see some OHs in square brackets all over the place as well. And those square brackets are just shorthand for concentration, like I just said, which is always going to be in molarity. But those numbers are generally going to be given to you, or if they aren't, we're going to be solving for those numbers using our pH. So we'll come back to that other equation here in just a minute. So if we're given the H plus concentration, we just need to push the negative button and the log button, type that number in, push enter, and that will give us our pH. Now, over here right next to it is a pOH equation. And if we look at it, that equation is almost exactly the same. The only difference is that it's finding the pOH and we're taking the negative log of the OH ions there. So that is going to be the same process either way. And it is kind of important to remember that they are basically the same process because you're only going to be given the pH equation on your equation sheet. So you need to know and recognize that if it is asking you for a pOH and you have the OH concentration, then you just need to do the same thing. Take that negative log of that number. So next, well, how do they relate to each other? I promised you we would be able to convert between them, and we can. And it's pretty simple. The pH is plus the pOH is always going to be equal to 14. So like we saw over here, when the pH was 0, our pOH was 14. When the pH was 7, then the pOH was 7. If my pH was 8.2, then my pOH would be 5.8, and so on and so forth. So we can always calculate one from the other just by knowing that they will always add up to 14. Now, the last equations that we're really going to be using here are these hydrogen ion and OH ion equations, because like I kind of referenced before, well, what if I want to find what my concentration is if I know the pH? Then technically what we're doing, this is just an algebraic rearrangement of the equation up top. And you would actually have to memorize this or be able to get from that equation to this equation, because this equation and its kind of sister equation over here with the OH's in it are not on our equation sheet. And if you've studied logs before, because this is log base 10, the way that we undo that, kind of try and solve for that H plus, is by raising each side, or that log and the other side, to the power of the base. So because this is log base 10, we're raising 10 to that power. And then if we wanted to get rid, so that would get rid of our log. And then we still have a negative sign here, so we move it over there, and that would solve for our H plus. So if you know how to work with logs and do algebra with logs, then it's easy. Just, solve for H plus. If you haven't before, then this really is going to be a little bit of memorization, that we have to look at 10 raised to that negative pH if we're trying to find the H plus concentration. But that's actually going to be hopefully not too hard, because we're actually going to use that in what I call the exponent rule. And these first few problems are just going to use this rule on this page, where if I give you a concentration, which oftentimes is in scientific notation, so it'll be 1 or some other number times 10 to a power, if that base is 1, then 1 times anything is really just that other thing. So what we end up looking at is 10 raised to a power, and that is generally a negative number. And so basically what we're looking at here, whatever that number is going to be our pH because of this equation. So we're going to get used to looking for our pH up there in some of these simple problems, and so that can kind of help us remember that that's all I need to do. 10 to the negative pH will get me my H plus concentration. And of course, in the same way, if I do 10 to the negative pOH, that will get me my OH concentration. Now, we're not going to use this equation over here very much. We technically can, and that just will help us if I want to convert from one concentration directly to the other. If we multiply them together, they're going to be equal to 1 times 10 to the negative 14. And remember that you can plug that number into your calculator as 1e negative 14, and that'll help solve for things a little bit easier. So this is kind of a whole mess of equations here. I want to try and get them a little more organized in a map. So taking those, the pH side of things, going back and forth from pH to H plus, we either are using the pH equation. If we have our H plus and we're trying to get to pH, then we'll use this equation. If we have our pH and we're trying to get to H plus, we're solving for the H plus using that equation. And between our pOH and our OH concentration, we can use those kind of very similar formulas to get back and forth. Now remember that the easiest way to get back and forth between these two sides of this map is the fact that the pH plus the pOH will always equal 14. And this is usually as much as I use. Like I said, I don't really like that scientific notation equation over there, but if I am trying to get directly between these two, then it is useful. But even if I had to get from pH to OH, I would choose to go this direction to get there because it's easy for me to subtract from 14. It's easy for me to remember to take the 10 to the negative power. Those are things I do all the time. Go in this direction, even though it should get me a similar answer, is harder to remember and involves more buttons to push with that scientific notation. So this is our map, and you can technically go two directions, two different paths to solve any of the problems that we are working here. It's just some of them are quicker than others, and because of that, some of us might be getting slightly more different answers than we're used to. So as long as your answers are pretty close, you are fine. And as long as you show your work as you're doing that on a test or a quiz, you will get full credit for doing the work your direction, even if my default is another direction. So let's actually give some of these a try. I've got all of those equations up at the top. And in this first set of problems, since we're trying to get from H plus and solving for pH, you might think that what we would be using is our pH equation. But in these first few problems, like I said, what we've got is this special case where I have 1 as my base. So really all I'm looking at is 10 raised to a power, 10 raised to a negative number, which means that I'm looking at something that looks a whole lot like that H plus equals 10 to the negative pH. So if I know that's my H plus concentration, and I have a whole number up there in that exponent waiting for me, then our pH is going to be that exponent. So I know the pH of the next one is 6. And that's all that I have to do is look at the itty bitty little exponent up there. As long as that first number is 1, that is my pH value. So now I can use those pHs to tell that this first solution is a base because it is bigger than 7, and my second solution is an acid because that is less than 7. So pretty quick, no calculating involved. This next set, we still have some of those special numbers that are 1 times 10 to some power. So I'm still going to be using my exponent trick. But notice here, because I'm given my OH concentration, or I'm given a concentration of something that has OH in it, this is essentially my OH concentration, because every one of those NaOHs, when it breaks up, is going to make equal amounts of Na and OH. And for every one of these molecules, I'm making one of those ions. So this concentration that I'm given here is the OH concentration. So if I'm looking at that little negative exponent, because I'm starting with an OH concentration, that exponent is my pOH. So we can bring those numbers over, but that's my pOH number. And if I want to tell what type of solution this is, I need to be looking at the pHs. So if I subtract from 14, because we remember that pH plus pOH is going to be equaling 14, then 14 minus 5 is 9, and 14 minus 8 is 6, which, oh my gosh, even though those first numbers look different, these are actually the exact same types of solution, the exact same pH solutions as we were working with in number 1, just didn't look quite the same because the numbers we were given are different. But this is still a base, and this is still an acid because our pH is bigger or less than 7, respectively. So, moving forward here, let's try and go backwards. If my pH is 4, and I want to find my H plus concentration, then we're going to be doing that H plus is equal to 10 to the negative pH. And so you're going to be writing down or thinking this is 10 to the negative 4. And it is, but that's not really the proper way to put our answer together. If you put that in your calculator, it's going to give you an answer that either looks like this in scientific notation, or 1, 2, 3, there we go, that. And this is a perfectly acceptable answer as well. It's the exact same value as this. It's just not in scientific notation. So that is our molarity of our H plus at that specific pH. Now, if I do the same with the next one, that is definitely going to stay in scientific notation. My calculator doesn't have enough space to put those decimals in it. But all I'm doing is 10 raised to the negative 7. And putting it in proper scientific notation just means that we need to have a base of 1 up in front of that nice 10 to the negative 7. So now let's do the same going from pH to OH concentration. And because my H and my OH don't match, then I can't just use my exponent rule here. I'm going to have to turn my pH into POH first, and then I'll be able to turn it into the OH concentration. So 14 minus 14 is 0, and then 14 minus 2 is 12. So those are my POHs. And now that my ions match, it's OH and OH, now I can get to that concentration more easily. So our OH concentration is just going to be 10 to the negative of that POH. So 10 to the, well, there's no negative 0, but 1 times 10 to the 0 is my answer here, although anything raised to the 0 is 1. So that is 1 molar. And then 1 times 10 to the negative 12th is the molarity of that second solution. So hopefully that got you used to some of the simple conversions that we can do. And all we need to focus on is having that base of our scientific notation equal to 1. If we have nice whole number pHs and POHs, or if we are given nice concentrations with that base equal to 1, then we can use that exponent rule to find our pH and our POHs. But what we're going to do in the next set of problems are kind of the same things we were just talking about, but these aren't going to have nice, neat whole numbers here. This isn't going to be 1.00 anymore. So because our base isn't 1, we can't just use the exponent rule. It's going to be close to whatever that exponent is, and that's a good way for you to check your answer or eliminate options in a multiple choice test. But if the base isn't exactly 1.00, even this 1.45, not close enough, our answer is not going to be exactly 9. So we are going to have to push some buttons in the calculator in order to get these answers. So remember our map here and kind of what calculations we're having to do to get to each place. So here, going from H plus to pH, when I don't have my nice, neat, even 1 times 10 to the negative 9, that means I am going to have to use my pH equation. But all I've got to plug into my calculator is negative button, log button, probably has a little open parentheses built into it, and I just need to type this number into this space. So in our calculators at school, you can either push 1.45 times 10 raised to the negative, which is down there. It's not the subtraction sign, and same up here. It's the negative sign that's down by the decimal point. And then 9, and then close parentheses equals, or you know that my preference is to use the E button. It's a lot fewer buttons than what we had to push there. We can just push second x minus 1, and that gets our big capital E in here. And then we can just make sure that that exponent is negative 9. Much simpler to type out. Either way, when you plug that into your calculator and push enter, then it's going to be giving you 8.84. And we're going to round this just the best that you can to be equal to the number of sig figs in the base from that original concentration. So I rounded this to 3 sig figs here. And you notice it's pretty close to 9. It's not too far off, but it isn't exactly 9 anymore. If I do the same thing with this concentration down here, just taking the negative log of this number, then I get 5.70. And even though these are decimal numbers, we're thinking about the type of solution, then this one is bigger than 7, so it's a base. This one is less than 7, so it's an acid. Moving on to our next type, trying to get to the pH from the OH concentration. When we take that negative log of these numbers, these concentrations we're given, and anytime we're given a concentration, your instinct should be to take the negative log of it, get rid of all that crazy scientific notation. But because we're starting with OH values, that's giving us our pOH here. And so once I get that value, if I was actually looking for our pH, then I'm going to have to do 14 minus 4.60, and that is going to get me my 9.40 pH and 10.65 for that second one, which does mean that this is both. These are both going to be base solutions, because they're both bigger than 7. So almost done here. Trying to get from pH to H+. Remember that we said all we need to do is take that pH and put it up in the exponent area. But in scientific notation, we are not allowed to have exponents that are decimal numbers. They have to be whole numbers. So even though what you'd like to write as your answer is just 10 to the negative 4.15, or possibly 1 times 10 to the negative 4.15. That is not proper scientific notation. So even though that is technically our answer, that's the correct value, because we can't report our answers in this way because it's not a pretty number, the way that the scientists say scientific notation should be done, what we need to do is put it in our calculator that way. Just in our calculator, 10 raised to the negative 4.15, and then push enter equals, and then that is going to give us our final answer here. We have to report our numbers, our final answers, in proper scientific notation, which means we cannot have a decimal here. So yet again, one of the things that happens when I have kind of messy numbers is I have to use my calculator. But the calculator will do that work for you. You just have to remember, just like when they were prettier numbers, to do 10 raised to the negative of that pH, and the calculator will do the rest. So if I do the 10 raised to the negative 7.23, then that gets me 5.89 times 10 to the negative 8. Last set of problems here, and we're just trying to get all the way from pH to OH concentration, and I actually didn't put that middle step in for yours. But even if all you're asked for is the OH concentration, when you see that our pH is not that ion, this is H and this is OH. If they don't match yet, then we're going to have to take a step in between to get them to match. The only thing we can convert directly between is the pH and the pOH. So subtracting from 14 tells me that my pOH here is 0.68, and down there it's 9.44. And now these numbers are ready to do our 10 to the negative pOH in order to find those OH concentrations. So 10 to the negative 0.68 is 2.09 times 10 to the negative 1, and 10 to the negative 9.44 is 3.63 times 10 to the negative 10. So lots of numbers to deal with, but when it comes down to it, using this map in order to kind of keep your brain organized as to where are we going, where are we starting, what calculation do I need to do to get there? Do I even need to do a calculation in the calculator, or can I do it in my head? Is going to be very useful because there's so many different types of problems, like you can see, that we just worked out on this page. So next class we're going to be working more on this idea and seeing some pHs in person.